Right. So I decided to take some time to write all the terms that we're going to be discussing. So I've written more than 30 terms. So let us continue. So we just finished this thing, structures. Now, the other skeleton I did not mention yet are the cyclos, okay? The cyclos. Now the cyclos are just rings, like we said. Now, basically, the smallest type of ring you can have is one that has three carbons, right? So that's going to be a prop, right? In this case, this will be a propane with a double bond, a propane, exactly. So we can also have butane, this acycloalkane. Remember, I call them ali. This is alicyclic. Now, why are they alicyclic? I said because they are aliphatic and also cyclic. So as they are, they are non-aromatic. Exactly. This guy, we can also have this is a four carbon ring. You can also have a five carbon ring. Okay, you can have a five carbon ring. That will look something like this. Okay. So, and of course, we also have heterocyclic rings. So, for example, if I were to just add an O here, maybe I have my four carbon ring, and I add an O here, for example. This is heterocyclic, okay? I believe there is a special name for those that have five rings. They call them furans, okay? Furan. So in this case, if it's this is actually the skeleton structure for the base structure for furanose, five carbon sugar. So furanose will be the name of this sugar by the time I add the other guys, okay? The general name for any such carbon, any such sugar that has this as its base structure. So then there's also piran. So in this case for sugar, it will be pyranose, okay? That's a five carbon ring, but that looks like a six carbon, okay? And you recall in the video where I discussed, I will link that video in the description, where I discussed structure with you. I also told you that this structure, this hexa, for example, this is cyclohexane, okay, another volatile alicyclic hydrocarbon. As it is like this, I told you that this is the general conformation that we give to it. This is also the general conformation we give to it. But actually, we know that in reality, in fluid form, for example, they don't take this conformation. They take what is called the chair conformation. So, for example, if you wanted to draw the chair conformation of this guy, which actually looks like this guy at the end of the day, except that this one is heterocyclic. This one is going to look like this. I taught you how to draw it. You just draw two lines here, put a dot here and put a dot here, down here, and join them like this. Do you understand? So it doesn't have to be perfect. It just has to, communicate what you're trying to say. So in this case, you can see already that this tells us that these are the parts where we can add our substituents. Is that okay? These are the places we can add our substituents. Do you understand? So if I wanted to add substituents, or maybe just show the hydrogen attached, So let me add the substituents, Br, H. So basically, these are just structures, the different skeleton structures that we can have. Remember, the vertices represent the carbon atoms. So except in an heterocyclic carbon, the atom will not be shown, okay? So the atom is shown here because this is heterocyclic. This is a different thing entirely. Is that okay? Another one is, so this one is called a pyridine. I'm sorry, a pyranose rather. Pyranose. Pyranose because it is sugar, okay? If it's a nitrogen, it will be something like this. It will look something like this. Pyridine looks something like this. Okay? So this is pyridine. This pyridine. In this one, this pyridine, there is 1, 2, 3, so it's balanced, it's correct this way. So this one is pyridine. Of course, you can also have a thiophene. There's also a thiophene. I'm just showing you the several structures that we can have. So this is going to be thiophene. Thiophene. All right, so that will be it. Now let's go to naming. That's the next thing, naming. So in order to name, the first thing I want you to see, let me draw a structure here first. Now keep in mind that I'm going to be using skeleton structures for the molecules that I want to name. But I'll first show you something, how to, demystify it. So look at this guy now, for example. Then you might be thinking that we shouldn't start with something complex. Actually, this thing is not complex. It's not complex at all. Right, so just watch. Let's say I wanted to maybe put a double bond here, then let's put a nitro group here. Let's put a carbonyl here. All right. So now, how do we name this, for example? So the first thing is, okay, let's add a substituent here. The first thing we want to do is identify the longest carbon-to-carbon chain here. The longest carbon-to-carbon chain. Now in this case, it's quite obvious what the carbon-to-carbon chain is. Now what I'll do is, let me first show you what this is. I'm going to draw out the full structure, okay? I'm going to try to expose the full structure. Display it, okay? So this will look like CH3 here, bonded to C, bound to carbonyl, bound to C that is bound to a nitro group, bound to CH2, bound to another CH2, bound to an sp2 carbon, bound to sp2, another sp2, bound to an sp3 carbon that is bound to a substituent chlorine, and then a thiol. So this thing that you are seeing here, this is a full structure here. Is that okay? Then I now have to put my hydrogens. So if I don't put the hydrogen, they are implied, okay? So this structure you are seeing here, this is primarily what it is, okay? So I am going to name this one, okay? But in further cases, in the next examples I'll give, is just a skeleton I'll give you and I'll name, okay? Because with the skeleton, we're also going to discuss radiochemistry. It's part of what I wrote down here. All right. So now, how do we name this guy? So you have to know this. Now you should draw this table that I want to give to you down. Now you should draw it down. I'm going to give you the order of priority for each family of hydrocarbon. So when you have several families here, for example, we have nitro group, we have this is ketone, this is a ketone, this is alkene, okay, and then another substituent here. So when you have something like this, which one should take priority? So that is what we want to discuss now. Which one should take priority? So look at this table. This table is going to help you a lot. All right. So make sure you put it down. So we have their name. I'll give you their name then. I'll now give you their functional groups. Now, this functional group, let's be a little wider. Now, you will use them as suffix if they take the highest priority. You use these suffixes if they take the highest priority. Okay, but they will take the following prefixes if they have the lowest priority. All right, that is, what do I mean by lowest and highest priority? So in a case like this, where you have a nitro group, a ketone, and an alkene, which one will take the highest priority? Which one will I give more? Which one will take the, the one that has the highest priority is the one that takes the ending, the name usually takes the parent chain usually has the parent's name that will give it, the last name that will give it. It ends in the family name, okay? So the one who will give the priority here is the one that will determine that parent's name. Exactly, that's what I mean now. This one, the one who give priority is the one that will give the parent's name. So the others will either become become substituent or lower functional group. All right, so now watch. We begin with the one that is given the highest priority, which are the carboxylic acids. The carboxylic acids. Carboxylic acids. So, of all the hydrocarbons, of all the organic compounds, functional groups rather, these guys, this family has the highest priority. Is that okay? And their functional group looks like this. COH. Is that okay? COH. So that's the functional group. Now, when they appear, when they are given the highest priority, of course, the name will end with oic. That is, the parent name will end with oic. Usually oic acid. Is that okay? Oic acid. So, but of course, if they have a lower priority, which in majority of the cases, or almost all cases, in fact, all cases, because those are the cases for the cases I have seen, okay? But of course, if they would actually take any prefix, it would be carboxy. Is that okay? Carboxy something. Exactly. Then the next one is the sulfonic acid. The sulfonic acid. These ones also have a good they are very strong. Okay, not necessarily the strength. It's actually because of it has been there are many factors that we consider before they give them these priorities. Okay, electronegativity, um, I think the size of the molecule. No, basically just know this sequence. Know this sequence: carboxylic acid, sulfonic acid, then after which we now have esters. Let me list them first. We have the esters. Then after that we have the amides. The amides are the next. Then after which we'll have, that was why I was contemplating on whether to write that one in order of complexity before, because I know I will still have to give you this table. Okay, so we have amides. So before amides actually, we have acid chlorides actually. We have acid chlorides. So most acids are given priority. So ester is only just above this. And the reason why is because ester is formed from carboxylic acids. I mean, of course, we know the synthesis process, alcohol plus um, alkanoic acid to give ester. So acids are usually given priority, as you can see already. Then before the amides, actually, before the amides. And after an amide, then comes the nitrile. Okay, the nitrile. Then after the nitriles, we have the aldehyde. Then after an aldehyde, we have a ketone. So in a group where you have aldehyde and you have a ketone, which one will you give priority to? You give the highest priority to the aldehyde. Now, you also notice that, actually, you should also know that usually we give priority to guys that have terminal functional groups. Okay, the guys that have you notice that most of these are terminal functional groups. Is that okay? Terminal functional group. This one is non-terminal, though. Ester is non-terminal. This guy, terminal functional group. So they are usually giving the highest priority. Okay. Then after ketone, we can now have our alcohols. Okay, the alcohol. Then after this, we'll have the amines. Then after which come after amines, we have the which other one? Alkynes now. Alkynes. Then alkenes before alkynes. Sorry, the alkenes have higher priority than alkyne. Now you should see my video on alkyne. I'll link it in the description. I discussed naming on this. Okay, but I'll probably give an example here again. You see this alkyne and alkene. Usually we only give alkene priority in a case where there is need for a choice. But there are some cases where you will give priority to alkyne over alkene, and maybe I'll probably show you an example here. Then before alkenes, then before now have which one again now? Then we have the ethers, of course, ethers, then halogens. The one that have the lowest priority is the nitro group. The nitro group. So they have the lowest priority. Now let's talk about their functional group. So what that means, what this means is this, that if you have an amide and a ketone, you give amide the highest priority. It will be the one that will bear the final name, the family name, okay? That's what we call it, the family name, the last name that you usually end it with, right? That's how to know it, right? So for example, this one, we have aim to end it, right? I'm to end it, in to end it. Okay, no, we are still going to discuss it, okay. So look at it here. The functional group of this guy is SO3H. I think we discussed this under benzene as well. These guys, esters, we have COR, then acid chlorides. The acid chlorides, their functional group is CO, then Cl, chlorine. Amide, we have CO, then NH2. Then in nitrile, we have C triple bond, then aldehyde. Now, for this guy, I've had a student tell me that he has seen something like this before. Actually, I told the student that now, when carbon is usually double bound to triple bound to N in a nitrile. So we're saying that this is also a nitrile, okay? Now, in a nitrile, this is a nitrile. The moment you see this, then there's definitely an H here. Okay, there's definitely going to be an H here because around every nitrogen there must be 3 bonds. Okay, so we have 1, 2, then 3. The third one is to hydrogen. But another thing is what I explained to the students is that if these are occurred, then maybe they are showing you what is called. We are going to discuss it. I think under electromeric effect. So where maybe there is an approaching organogen, so that the bond, this double bond, collapses on this guy, such that this guy now has a lone pair. Exactly. Actually, it already has a lone pair here. But by the time this guy collapses on it, to have 2 lone pairs. Why? How do I know it has a lone pair here? If you count the octet? If you count the octet structure, it's going to look like this. It's going to look like this: 1, 2, 3, 4, 5, 6, 7, 8. Exactly. So that's how I know that I told you that it has a lone pair. Good morning, sir. Yes, sir. So, like I was saying, so that guy, I'm able to tell if it has a stable octet. So I know that then there must be a lone pair here. So for this lone pair, we are also going to talk about charges, okay? For this, but is not charged, okay? So by the time you now have a double bond here like this here, it's going to have, the lone pair would have collapsed on it. That's what I mean now, okay? This, I'm going to show you what mechanism is. I hope I wrote mechanism too. Mechanism, let me add it here. We'll talk about mechanism, an arrow, mechanism. Okay, so like I said, this guy, this bond has collapsed on this guy such that there are now 2 lone pairs here. There are 2 lone pairs. So this guy will now have a formal negative charge. So I now told the student that this is still nitrile if there is a negative charge. So there must be a negative charge here. So otherwise there will be a nitrogen here. Exactly. So that is excuse me please. So that is nitrile for you. That's nitrile. Okay, I was just trying to lay emphasis on the fact that nitrile is carbon triple bound to nitrogen. Then aldehyde, we have CHO, that is C double bond O and H. It's terminal. Then this guy is CO, okay. CO like that. That's C double bond to O. Then alcohol is OH, ROH. Then amines is NH2. That is like that's NH2. Then alkenes, we have double bond C, Alkynes, we have C triple bond to C. Alkanes, we have C single bond to C. Ethers, we have O like this. Is that okay? That's O, right? ROR. Then halogens, we have X. Then these are actually not functional groups. This one's from here, from this guys down, is not functional group. They are just substituents. Okay, but nitro is this. Alright, so here's now my point. Now, what is the suffix for when you have a carboxylic acid? Of course, you end it with what? Oic acid. That's what I'm saying. At the end, the final name of what? Oic acid. If I added a carbo, for example, if I come here now and turn this into double bond O and OH, this name will definitely change. It will definitely favor the direction of this guy already. Do you understand? It means that because I've added a carboxylic acid now, I begin to count from this direction, no matter what I've had before. Is that clear? But let's first change it back to what I had initially so that you know how we give priority according to what I just gave you here. Then this one, of course, it will end with sulfonic acid. That's the name already. So it will end with sulfonic acid. This one will end with oic acid, sulfonic acid. Then this one, ester, is going to end with O8. You already should know that. The other one is quite common. O8. O8. Acid chlorides. Acid chlorides end with I think it ends with, when I remember I'll tell you. I think it ends with no, the prefix is chloro. Let me go to this first. If I remember, I'll let you know. Amides, they end with amide, of course. They end with amide. And they take the prefix. Maybe if I'm writing the prefix, I remember. These ones take the prefix. This is a formula. Okay? So, this one, okay, I think this one is chloroformyl, right? This one is chloroformyl. Alright. This one is chloroformyl. So this is another formula here. So this will be this one is going to be why am I forgetting this thing? This is going to be nitrile. Like I said, this one is going to end with nitrile, but it will have the prefix cyano. Okay? This one will have the prefix cyano. This one, why am I forgetting now? Amide group. Their prefix. Come back quickly. Okay, let's continue. This one, of course, we end with al because it's alkanal, you remember? This one alkanone, so on. Then this one is a formyl, so formyl. Then this one alkanone will be an oxo group. You understand now for the prefix oxo. This one, amide and this one, all, okay, all. This one, amine, or amino, sorry. No, suffix will be amine. Then this guy will be amino, okay. Then for this guy it will be hydroxy, not hydroxyl, but hydroxy. So chloroformyl. Yeah, I think it's chloroformyl, not chloroformyl. Chloroformyl. Then okay, yeah, is this one I'm trying to remember? This one, okay, sorry. Even before an alkene, there is a thiol group. Before an alkene, there is a thiol group. Or is it before amino? before an alkene, yes, there is a thiol. Okay, so a thiol has the formula SH. Okay, thiol group. I mean, of course, the suffix should be thiol, and the prefix is mercapto. Then, then, um, then alkene, of course, you already know that. In, alkyne, ein, alkane, a, alkane, a. Then the ethers, they have a suffix. They generally don't have suffixes. So these ones, they are not functional groups, like I said. So for the prefix of alkene, I mean, it will still be N, ein, I'm going to give you an example of what I mean. I'll show you an example of what I mean. So these ones, how did I forget this? Imide group will be, I cannot begin to search now. Imide. The prefix of imide will be, let me quickly look for it. Alright, so please forgive me, I've found it. The prefix for this one, the suffix for acid chloride is oil chloride. Sometimes when you face the camera, everything just dissipates. Oil chloride. So then chloroformyl, then this guy is carbonyl. That's amide. That's it. So then, of course, this one, the suffix of this one, wait, is alkoxyl carbonyl, and this one is sulfur. Why didn't I write this before? This is sulfur. Alright, so that's it. I mean, the rest, this one will be chloro, bromo as it applies, nitro as it applies. So, alright. This one now will be oxy, okay? Oxy, depending on what it is. For example, it could be methoxy, ethoxy, whatever it is for ethers. That's for the prefix. Is that okay? Alright. Now let's go to this now. Let's go on to naming this. Now, how do we name this? We number the longest carbon chain, which is exactly this. In this case, it's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right. So since it's 11, that's what on deck. Okay. So then we now have which functional group has the highest priority here? So of course we have double bond here, and we have carbonyl compound here. So that carbonyl there is higher than double bond, right? So it's going to get the highest priority. So we'll number in the direction that will give this guy, the lowest number. So we have 1, 2, 3. So we'll approach this guy on 3. 4, the fourth functional, so this one becomes a substituent, So the fourth substituent will be found on carbon 4. So that will be 4 nitro. The second one, so we have 2, 3, 4, okay, 5, 6. The second functional group will be carbon 6, 6 chloro. Alright, so which one should come first? The C comes first. So, I mean, this thing is not correct. Okay. So 6 chloro, C comes first before N. So we are going to pick the N, write the C first. Alright, but of course, how will it end? Now looking at this is N, right? It's on carbon 4. On carbon, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm sorry. What am I numbering? 9 chloro. This guy, the N falls on carbon 7. So, dec 7 and dec 7 and 3 ohm. So keep in mind that, so we said the family name will end with that one that has the highest priority, okay? So 3 ohm. So our answer becomes 9 chloro, keeping in mind that dash between number and letter, 9 chloro 4, 9 chloro 4 nitro on dec 7, on deca 7, deca 7 and 3 ohm, not deca 7 and 3 ohm. That, well, the R here is just for pronunciation, okay? Pronunciation 6, so that it can make sense. Deca 7 and 3 ohm. And 7N shows us that the double one is on carbon 7, and 3 ohm shows us that the carbonyl group is on carbon 3. All right. So now let's now name other molecules. Now let's name other structures. So look at this one. What we wanted to name this? Now looking at this, how do we name this guy? Let's put. Now looking at this guy, if you look at it very well, you will see that if you go now, the first thing you should identify is the family with the functional group with the highest priority. And what should that be? That would be a carboxylic acid, C double bond OH. This is that C double bond OH. Do you understand now? So this guy is the highest priority. So this guy must be part of the parent chain, and it is terminal. So since it is terminal, any other group that is emanating from it is going to be a substituent. Keep that in mind. Keep that in mind. Any other group that is emanating away from it is going to be what? A substituent. So how do we count here? There are two ways we can count. Is that we count like this: 1, 2, 3, 4, 5, 6, right? The last carbon here. Now looking at here, if we count like this: 1, 2, 3, 4, 5, 6, we still get 6. So which direction should we pick? Now the truth is that we are going to pick this direction. Why? Because there are other substituents here. Do you understand now? So because of that, this one becomes our lower priority. This one becomes a substituent. So what substituent will this be? This will be 1, 2, 3, 4 on this carbon. 1, 2, 3, 4. So that will be what? Butyl. Is that okay? So we are going to number from here first. 1, 2, 3, 4, 5, 6 carbons in total. Giving this one number 1. Giving the next substituent number 2. This becomes the substituent. This becomes the substituent. Is that clear? So now, given that, we have that this guy will have our first substituent on carbon 2. This being our family name becomes oic acid, right? Our name is going to end with oic acid. Then the first substituent we approach it on carbon 2, so that will be 2, 1, 2, 3, 4 butyl, 2 butyl, okay, 2 butyl, 3. What do we find on 3? C double bond O. Now you have 3 C double bond O being a substituent rather than a functional group. It will be a prefix. It has lowest priority, so that will be oxo. So this becomes 3 butyl, 3 oxo, 4, 5 methyl, 5 methyl. All right. So as it is, how do we now list? So we list in alphabetical order. This comes first, this comes next. So the answer becomes 2 butyl, 5 methyl, 5-methyl, 3-oxo, 3-oxo. That's all. 3-oxo. How many carbons do we have? 6 carbons, giving us hexanoic, right? 3-oxo-hexanoic acid. So there is never anything like hexan-2-oic, hexan-3-oic. No. Except if we have the functional group appear twice. And in which case, watch. In which case it might look confusing. So for example, look at this. Look at something like this. You have something like this, COH. For example, you now have it here as well. Let's say you have it here as well. COH. Now if you have something like this, your parent chain is going to be like this. Okay? It's going to be carbon 1, 2, 3, 4, 5. 5. So we have carbon 1, 2, 3, 4, 5. So what does that tell you? This becomes a substituent, this also becomes a substituent. Exactly. So our substituent becomes the first substituent will appear. We could go like this too, okay? Okay, yeah, let's go in both directions. 1, 2, 3, 4, 5. So which direction is going to give this guy the lowest? Now this one is a bigger group, right? So I'm going to give it a lower priority than this, okay? A higher priority rather than this. So this is the best direction to number in the best direction. So this is 2-ethyl. This is 2-ethyl. Then the next one will be 4, because we are using this number here, this numbering system here. 4-methyl. But because they belong to the same group, usually, whether you use 2-ethyl, 2-methyl, 4-methyl, I think the answer is still the same. Is that okay? Especially given that the functional group is this guy. So this becomes 2-ethyl, 4-methyl, 2-ethyl, 4-methyl, or 4-ethyl, 2-methyl. Is that clear? Because they belong to the same group, okay? But I'm giving it this way because this one is bigger. The ethyl is bigger, so I'm giving it a priority. I'm giving it 2, the lowest number. I'm giving methyl 4. So like I was saying, 2-ethyl, 4-methyl, then how many carbons do we have? 5. So that will be pent, right? Now, pentan, tan giving us single bonds all through, right? And is what gives us the notion of single bonds all through. Okay? And, not and. Okay? Single bonds. So we have and 1,5 dioic acid. Is that clear now? So that is what I am. So the name becomes 2, E comes before that guy, 2-ethyl, 4-methyl, pentan, 1,5-dioic acid. Alright, is this clear now? Alright, then I said I was going to name one with alkene and alkyne together. Okay, now let's do that here. Let me give that example here. So for example, what if I have something like this? Now what if I have something like this? So if I number in this direction, I will encounter, let's do it this way. You know what? I want you to see a situation where I will not have a choice than to give the alkyne the lowest number. Because here I've told you that alkene have the highest priority, right? But look at this, if I number in this direction, I will have 1, 2, 3, 4, hit double bond on carbon 4. Then 5, 6, 7, 8, 9, 10. Now, keep in mind that I said you should put dots. I've already told you before that you should put dots in a linear molecule here like this. So I now said that this guy here would be we have the lowest number if we go in this direction. But if we come in this direction, we have carbon 1, carbon 2. We'll meet the double bond on carbon 3, carbon 4, carbon 5, 6, 7. So if we want to list the, we want to give the numbers, if we want to name it, carbon 2, a double bond will fall on 4, triple bond will fall on 4, 5, 6, 7. If we name in this direction, double bond, triple bond will fall on 3, double bond will fall on 6. So which naming system do we use? We are going to use this, of course. Do you understand? Now we are going to use this. Now the only place where we have to give priority to our king is where, if we come like this, look at this case, look at that case. You know, of course, now that I said, according to this naming here, we are going in this direction, so we are using this. Exactly. But what if it were like this? So in this case, our carbon 1, carbon 2, carbon 3, carbon 4. So triple bond will be met on carbon 4. So this will be carbon 5, this will be carbon 6, carbon 7. So double bond will be met on carbon 7. But if we go like this, we have 1, 2, 3, 4, 5, 6, 7. So, okay, fine. So you are saying now that if we go in this direction, we'll meet on 4 and 7. If we go in this direction, we'll meet on 4 and 7. So this is where priority now comes in. So this is where you will now have to go in this direction, because whichever direction you go, you still get 4 and 7. So this is where you now pick for our king. You now give the double bond to double bond the priority. So the double bond will now have the lowest possible number. So we'll now go with this. Is that clear? Because if we come in this direction, triple bond is the one that will get the lowest possible number. But all the way, both numbers, either ways, both direction gives us the same set of numbers, right? So since we have that kind of case, we will now give our king the priority such that it has the lowest possible number. Is it clear now? So the name of this guy, therefore, will be this one, this particular one, will be, we have 5, 6, 7, 8, 9, 10, 11. Again, on. So this will be, there is no functional group, there is no substituent attached. So this will be on deck, on deck 7. Now we are going this direction. That will be 4. And but keep in mind that it will be is a 9 group, okay? It's always n before I. That is, the en will come before yne. So it is an N9 group, not an ene or whatever group. Is that okay? So this is the correct form of meaning. So deca 4n 7 I. On deca 4 and 7 I. Alright, so that will be it for naming. That will be it for naming. Now let's proceed to the next thing. Let's talk about intermolecular forces. Let me clean the board. So let's talk about intermolecular forces. That will be number 10. Intermolecular forces. So basically, this is talking about the forces of attraction and or repulsion between the molecules of the atoms inside a molecule. Okay, so when we have let's say, for example, I'm talking about a case where if I pour like, for example, I want you to be able to visualize it. Okay, if I pour alcohol into this thing now, what are the forces of attraction and repulsion that are happening here? You understand? What are the forces that are holding the molecules together, or that are coming in between the molecules, each molecule? So that's why I call it intermolecular forces. So there are 3 of them that you should know. There are actually 3. There are only 3 types of intermolecular forces. We have the LDF, okay, which stands for London Dispersion Forces. I've explained this too in the other video, so I'll link the video in the description again also. Now we also have the van der Waals force, van der Waals forces. I'm sorry, that is another name for it. The van der Waals forces. Intermolecular forces are also LDF forces are also called van der Waals forces. Now the first thing you should know is that the reason why I'm listing them like this is because it's the weakest. It's the weakest intermolecular forces. Intermolecular force. First, what is, we call them IMF. What is the effect of intermolecular force? See, one of the first things you must know is that it impacts the physical properties. Okay, I'm practically saying that the physical property of an organic compound depends more on the physical properties, depends more on the IMF, the intermolecular forces. Okay, physical properties depend more on IMF than the covalent bond or covalent nature. Okay, the physical properties depend more on what? On IMF than they depend on the covalent bond. In fact, they don't even depend on covalent bond. They primarily depend on the intermolecular force. So that's why we are studying it. Okay, and you soon see the effect now. You soon see what I mean by that now. Now, it is the weakest intermolecular force, and it occurs between non-polar molecules, okay, where we have non-polar compounds, non-polar compounds. Like, for example, LDF is what you see in alkane molecules. You understand? You will see more LDF as an intermolecular force in non-polar compounds than you will see this second one, which is the after LDF. The second one is the hydrogen bond. Which one is in between? Dipole-dipole interaction. Dipole-dipole interaction. So now dipole-dipole interaction is stronger than LDF. Okay, it's stronger than LDF. And why is it stronger? It is because it forms a permanent partial charge. A permanent partial charge. And in a moment, we are going to talk about partial charge. In fact, while we are at it, the next one we should talk about is charges. We'll talk about the following immediately. So number 11, we'll talk about charges. And we'll talk about boiling points. So before that, with this, we are going to talk about boiling point now. Boiling points. We are going to talk about boiling points. Where should I put that? Let me just list it here. We'll talk about boiling points and melting points. All right. So now, listen to me. Like I said this one is stronger than LDF, and it's because of permanent partial charge that is induced. Partial charge induced in the molecule, in between atoms. Partial charge induced in atoms. Okay. Now, where does it exist? Okay, primarily it exists between molecules that. Excuse me. So, like I was saying, I said it's because of the permanent partial charges that are induced in atoms. Now, because some students might get confused at all, already. Now, let me talk about charges first. I'll come back to this in a jiffy. Now, you see, what are charges? You see, there are two types of charges. Of course, you know plus and negative charge, right? Positive and negative charge. Okay? So, there are two types. We have the formal charge, and we have the partial charge. So, this partial charge I'm talking about, I want to talk about it now. Now, you see, there is something that we also have to talk about now, which is also electronegativity. So, I can't deal with all of this without dealing with each of these things I'm mentioning now. So you have to understand electronegativity. Okay, it's also part of what I listed here. Electronegativity. Actually, from electronegativity, we're supposed to go on to bond polarity. But that will be. Let's first discuss all this sequence, then we'll go to that. Now watch. So formal charge and partial charge. First, when do we have a charge? Let's talk about sodium, for example. Sodium, this is sodium metal, neutral sodium atom. if sodium now, for it to become charged, if you want to react, what it will do is it will lose an electron. Once it loses an electron, it becomes what? Na plus. Once it loses an electron, right? It has lost an electron. Now you see this Na plus is charged, isn't it? And you will signify or represent that by putting a positive charge on top. This positive charge you are putting here is a formal charge. Is a formal charge. Why is it formal? Because it is a full charge. This one shows that there is a total removal of electron from hydrogen atom itself. That is, hydrogen has totally lost an electron. So that's why you have a formal charge. So it means that you don't have a formal charge until there has been what? A total loss of electron, or an electron has left one particular place. Okay, an electron has left a place. That is, that electron is no longer in interaction with one other atom. So to say, that is okay. The reason I'm talking about this now is one will be talking about cation and carbanion, which is what we'll talk about after this. So listen to me again. A formal charge is given or assigned only when the electron is lost or gained. Is that okay? When an electron is gained, for example, you assign negative charge to oxygen when it has gained electrons. How many electrons? 2 electrons. Do you understand now? So when there is no gain or loss of electron yet, there is no charge. There is no charge. Exactly now. There is no formal charge. But now when we have partial charge, now partial charge is an induced polarity. Okay? Partial charge is an induced polarity because of electronegativity. Partial charges, no, not an induced polarity, sorry. Partial charges come because of difference in electronegativity values. So which means you have to understand what electronegativity is. Bond polarity is induced polarity because of difference in electronegativity too. Partial charge is what is induced in a molecule where we assign partial charge when there is a difference in electronegativity. So for example, in a bond like this, like Cl2 bond will contain Cl bonded to Cl, right? In this bond here, the electrons are equally spread across the 2 chlorine molecules. So if I were to show this bond, you know, I told you that a bond represents 2 electrons, right? If I were to draw a box that represents the position of the 2 electrons, you see the 2 electrons sitting equally between the chlorine, the 2 chlorine atoms. This thing is just making noise. The chlorine is the electrons are sitting in between the chlorine confidently. That is, it's not shifting to one than the other. You still understand. But in the case where I have an R group, okay, I have an R group here. Then with my carbon CH2, then there is now chlorine bonded to it. Now with this, I'm going to explain something with this later, okay? But I want to show you that in this case, for example, if I were to draw the position, a box to represent my bond now, you see this line notation that I used there, I change it to a box so that I can show you the electrons that are inside. Now, the electron will not be sitting comfortably like this. Actually, in this case, though there is still a bond, but you will find the electrons somewhere around here. Now, what do you notice? The electrons are sitting closer to chlorine than they are sitting close to carbon. Now, what is the reason? The reason is because carbon has a lower electronegativity value than chlorine. In fact, apart from chlorine is the third most electronegative atom, because fluorine has a electronegativity value of 4. Chlorine, oxygen has a electronegativity value of, oxygen has a electronegativity value of 3.5, while chlorine has a electronegativity value of 3.1, I think. So you see they are very close to each other. You understand? So fluorine has the highest, is the most electronegative element. So you don't expect it to sit with another atom and share electron with that atom equally. So first, what is electronegativity? Electronegativity is just the pull on electron, the capacity of an atom to pull electron towards itself. So if I say an atom is electronegative, it means it has a high capacity to do what? To pull electron towards itself. To gain. You know, electronegative elements generally gain electron. Okay, they generally take electron. So when they now form a bond with another element, a covalent bond, they usually polarize that bond by pulling electron density towards themselves more than, so it means that the electron will be staying closer to the chlorine than they are to the carbon. So in a way, this carbon will seem deficient of electron because positive charge here shows that electron has gone, right? Formal charge here shows that electron has gone. But this is called a partial charge. When you have a sigma plus and a sigma negative, it's showing what? Partial charges. This sigma plus here is just for to show that a partial charge is induced. That is, electron has not totally left here, but electrons are not close to this guy so much. Electron, then here, partial negative here, and negative electron that you are seeing here is showing that electron is being lost. Okay? So for example, if I were to write like NaCl, let me give you this, let me ionize this. I want you to understand this in context. Na plus and Cl minus shows that Na has given up one electron to chlorine. Cl minus shows that chlorine has accepted one electron from sodium. Do you understand now? This one is formal, these are formal charges. Formal negative, formal positive. But this one is partial positive, partial negative. This one shows that there is no total abstraction of the electron. Only that electron pool is closer to this guy than this guy. That is, this guy is feeling like it is empty of electron, even though it is bonded. Okay? And the reason is because it is bonded to a guy that has stronger pull on electron. I'm using guy now. An atom that has a stronger pull on electron, we say the atom is more electronegative. Exactly now. That is more electronegative. Alright, so that is it. So that is what electronegativity is. The pull on electron that an atom has. The ability of an atom to pull electron towards itself. That is the electronegativity of that atom. Now, so what is now charge? Charge is basically what we assign. We assign formal if the atom is positive. If the atom, we are assigned positive if the atom has totally lost the electron, and we assign negative if an atom has finally totally gained an electron. Then we assign partial positive if the electron is less electronegative, and we assign negative, partial negative to the other guy because it is drawing electron density towards itself. Electron density means the cloud of electron. Do you understand? So inside the cloud of electrons simply means that orbital where the electron is, the space where the electrons are sitting. That is, the electrons are shifting closer to that electronegative guy than they are shifting towards the guy that is bonded to the electronegative guy. So that's that. So now that we understand formal and partial charge, let's now come back to this. A dipole-dipole interaction is basically a permanent partial charge that is reduced in an atom. Is that okay? And it is stronger than the LDF. It is stronger than the LDF. So you will find this one in what? In polar compounds. Polar compounds. Or at least compounds that can dissolve in polar solvents. So it means that this thing induces polarity. So dipole-dipole induces what? Polarity on a molecule. Okay, but this one is found in non-polar compounds and it is very weak. Okay, but there is something with this guy, the LDF. What that means is that the more polar, the more non-polar, the more non-polar is a compound is, the higher the LDF. Do you understand? The higher the non-polarity, the higher the LDF. Then of course, the longer the chain length, that is, you know that, for example, for alkane series now, like I discussed, alkane series, we have alkane, we have methane, ethane, like that. So let me use ethane. and compare it to octane, for example. Look at octane. This one has 8 carbons, this one has 2 carbons. So this one is going to be more non-polar than this guy. Do you understand? Because non-polarity increases with chain length. Is that okay? It increases with what? Chain length. So the longer the chain length, the higher the non-polarity, and of course the larger the surface area. The higher the surface area. So what that means is this. That is, since the more non-polar, the higher the LDF interaction, then of course the longer the chain length, the longer the what? The longer or the higher the chain length, the longer the LDF, the higher the surface area, of course. Once the chain length is longer, then there's a larger surface area, and of course the higher the LDF. I've also explained this before, okay? So make sure you see that video in the description. Then of course, then what if there is a higher branching? So the higher degree of branching now, the lower the LDF, because when there is higher branching, then there is lower surface area, and for that reason, there is lower LDF. Is that okay? For dipole-dipole interaction, the higher the branching now, the higher the dipole-dipole interactions. So let's just DDI for that. Then the third intermolecular force that you will learn is the hydrogen bond. Okay. Now hydrogen bonding exists. Hydrogen bond exists when hydrogen is bonded to either of these three. FON. That's what I asked you to remember it with. FON or NOF, either way. When hydrogen is bonded with fluorine, oxygen, or nitrogen, then we have a hydrogen bond. Now keep in mind that it is the strongest covalent bond. Strongest intermolecular force. Strongest IMF. Stronger than dipole, but dipole is stronger than LDF. Than dipole-dipole interaction. So, and hydrogen bond. Okay, I wanted to show this. Look at this. If I have a molecule of water molecule here, for example. Now, using this dipole-dipole interaction, we have that, how do we first show the charges on this guy? Oxygen is very electronegative compared to hydrogen. Hydrogen has an electronegative value of about 2.1 or so. And compared to oxygen, which has an electronegative value of 3.5 or thereabouts. So a bond will be polarized. I've mentioned this before. A bond would generally be polarized if the electronegativity value is greater than or equal to greater than 0.4. Is that okay? Greater than or equal to 0.5. So either it's greater than 0.4 or greater than or equal to 0.5. So if the electronegativity value is greater than this, the bond, if it forms a bond with, if two atoms form bond together, and the difference in the electronegativity value is greater than 0.4 or greater than or equal to 0.5, that bond will definitely be polar. Then now compare this size. This size is this difference is very, very large. Do you understand now? So because of that, this one will be highly polar. That's why water is a very polar solvent. Then this one, because the electron density will be towards this guy, right? So it will be partial negative. Then this one here, partial positive. So it means that this one will enjoy more electron. Oxygen will enjoy more electron availability than this one will enjoy. Is that okay? So this one will be partial positive. Okay, so what dipole-dipole interaction is just, so if I now have another oxygen atom, so inside water now, if I pour water inside a bowl, what I'm saying is that, if I pour water inside a bowl, so if I could pick 2 molecules of that water out, what you will see is this, they are interacting somewhat like this, so there's another water that will come around here, then we have a hydrogen, so that there will be an interaction, because it is partial positive, partial negative, partial positive. So another water molecule, these guys will now interact. You understand? Plus and negative will now be attracting each other. This one and this one too will interact. Is that okay? Or because of distance, and of course, what I mean by distance is that, you see, there is something about it. Now, like I said, this thing here is used to show dipole moment. That's what I was supposed to start with. It's used to show dipole moment. Now, one thing with this is that the dipole moment is facing this direction. The dipole moment usually faces the side that is more electronegative. That's the point. The dipole moment always is usually drawn to face the side that has more that is more electronegative. But I wanted to say that it also dissipates with distance. Okay, because of this, instead of this guy to interact with this oxygen here, this oxygen will rather interact with another hydrogen that is closer to it. Then this, so there has to be another water molecule here, so that it interacts here. So that this one will be partial negative, this one is partial positive, like we have been designating. Is that clear now? So this is dipole-dipole interaction, right? While then we now have hydrogen bond. So of course, actually, in the real sense, this is actually because this hydrogen to oxygen, this is actually hydrogen bond in water. What we actually see is hydrogen bond. Exactly. All we see is hydrogen bond. But the case is just that I was trying to say that this is hydrogen bond, okay? Oh, yeah, that's what I'm talking about. That this is hydrogen bond here, then this is dipole-dipole interaction. Is that okay? So this is hydrogen bond. Hydrogen bond occurs when hydrogen is bonded to fluorine, hydrogen is bonded to oxygen, hydrogen is bonded to nitrogen. So that is that. So that is that on intermolecular forces. So now what does this impact? It impacts on the boiling, it has impact rather. It influences the boiling point and melting point. Now keep in mind though that I'll emphasize more on boiling point, okay, because it's easier. I mean, more questions come on it than melting point, okay? Because melting point is majorly dependent on the molecular symmetry of the molecule and the packing efficiency, okay? The packing efficiency. But I'll be emphasizing on the boiling point, like I said, with these guys. So the higher the hydrogen bond, the higher the boiling point, okay? And of course, the higher the melting point, usually. So the higher the hydrogen bond, the higher the boiling point. I'll link the video in the description. I've explained further on these two before. So that's that. So you now understand boiling point, right? You understand charges. So a molecule like alkane, for example, is going to have a very low boiling point. When you compare an alkane now, if you compare an alkane to an alkyne, and compare that to an alkanol, the boiling point is going to increase as you go down like this. Even though alkyne and alkane for example, let's compare butane and butane, and then with butanol. So this guy is going to have a higher boiling point than these guys as you go up like that. Do you understand? Because of in butanol, for example, this is butanol, right? Butanol. So now what will happen is that you are going to have dipole-dipole interaction. Okay? So another butanol molecule will come here. So let's call this R. So another R group will come here and will orient itself in such a way that the hydrogen and the oxygen will interact. Do you understand now? They will interact because of dipole. The dipole moment is towards the direction on this guy. But of course, in this case here, because of dipole moment is towards it, then this is partially electronegative, so it's partially electropositive, so there's dipole-dipole interaction. So because of that, some more energy, I'm still talking about boiling point now, some energy we use to break this, then some more energy, extra energy is now needed to break the dipole-dipole interaction. So between this guy and another ROH. Do you understand now? There is dipole-dipole interaction. So after breaking this normal intramolecular force, then another extra extra energy is needed to break this bond. So that is dipole-dipole interaction for you. So that's why the boiling point of this guy is going to be higher. Okay? All right. And of course, the more polar the molecule, the higher the boiling point. So for example, butanol will not be as polar as butan 1,4-diol. Do you understand? So this one is going to be more polar than even this one. Hence this one will have more boiling points than, higher boiling point than this guy. Exactly. So that's just what I mean by that. Now the next thing is, we have talked about charges. Let's talk about degrees of solubility. Let me just quickly talk about solubility, because everything here they have to do with they are quite alike. Okay, I mean they are associated rather. So now keep in mind also that the boiling point will increase with, I said boiling point will, when I talked about branching, I said branching increases. The higher the branching, the lower the LDF. But the higher the branching, the lower the boiling point. Exactly. The higher the branching, is it the higher the branching, lower the boiling point? Branching, what does branching do? Branching do. Yes, the higher the branching, the lower the boiling point. The higher the branching, the lower the boiling point. So then for solubility as well. The higher the branching, the higher the solubility of any organic compound that I've been talking about. Okay, so a compound that has a very high boiling point, for example, butan 1,2,3-triol. For example, let's give an example of butan 1,2,3-triol. So for something like this, it's going to have a very high boiling point. Why? Because of this guy, the OH groups that are attached. So there will be more dipole-dipole interaction. And the higher the dipole-dipole interaction, the higher the boiling point. So this guy will have a high boiling point. Then of course, it will also have a higher solubility. It will have a higher solubility than corresponding, it will have a higher solubility, for example, than butanol, butan-2-ol, or butan 1,2-diol. Do you understand now? The reason is because this one has more centers for dipole-dipole interaction. I hope you're understanding me now. So butan 1,2,3-triol, of course, will be more polar than butan 1,2-diol. Do you understand? Because that one has only 2 centers for dipole-dipole interaction. Butan 1,2-diol. So the point is this, and that one, of course, will now be more polar than butan 1-ol or butanol. Exactly now. So that shows you that as the degree of polarity is increasing, the solubility is also what? Increasing. So polarity also affects solubility. Exactly now. So when you talk of solubility now, these ones will be non-soluble in polar solvent. These ones too, non-soluble in polar solvent. I said non-soluble. Insoluble in polar solvent. Insoluble in polar solvent. Well, this guy is going to be what? Soluble in polar solvent. Do you understand? Why? Because it is polar. So a polar solvent will be soluble in a polar solvent. So this guy can dissolve in water now. Exactly. But again, speaking of solubility, if you compare butanol and octanol, for example, octanol, now the surface area has increased, right? Since the surface area has increased, the solubility will decrease. So when you compare chain length and surface area, they are directly proportional. So an increasing chain length, then an increasing surface area. And an increasing surface area, a lower solubility. Is that okay? Higher chain length, higher surface area, lower solubility, lower polarity. Is that okay? Higher boiling point. Are you getting it now? All right. So that is it for that. So make sure, just do give those relationships. By the time you now find this thing, have questions on them, you are going to know how to relate them. All right. So that's that. Let's go to degrees of carbon and anions and ions rather. Carbon ions. All right, now let's talk about the degrees of carbon. Yes, and we are at number 16 because I've talked about many things that overlap each other. Do you understand? So that's why we have gotten to number 16. Now, degrees of carbon. Degrees of carbon, there are 4 degrees of carbon. We have the primary carbon. The primary carbon, we use 1 degree for that. Then we have the secondary carbon, of course. Secondary carbon. 2 degrees. Then we have the tertiary carbon. Tertiary carbon. That's 3 degrees. Then we have the quaternary carbon. Quaternary carbon. That's 4 degrees. Now, what do we mean by this? So for primary carbon, for a primary carbon is a carbon that is bonded to 1 more carbon. A carbon that is bonded to 1 more carbon is carbon bound to 1 more carbon only. Then the rest are hydrogen. Is that okay? It is bound to only 1 carbon. Another way to think of a primary carbon is this. There is only 1 substitution. Every other thing is hydrogen. Because I'm going to ask you, I'm going to give you a question now, and you will understand what I'm trying to say. Once the group that is attached to that carbon is 3 hydrogens and 1 different group, as primary carbon. A carbon is primary if it is attached to 1 carbon only, then the rest are hydrogens. Or a carbon is primary if it is attached to to 1 substituent and every other thing is hydrogen. So in as much as it's not hydrogen that is surrounding it, then the carbon is not primary. Is that clear? That is, if the hydrogen surrounding it, they are not more than 3. If there are 3 hydrogens surrounding a carbon, that's it. If there are 3 hydrogens surrounding a carbon, for an alkane now, that's for an alkane. If there are 3 hydrogens surrounding a carbon, then that carbon is primary. Is that clear? Okay? And don't worry, when I give examples, you understand better. Secondary carbon. Carbon bound to 2 more carbons. 2 more. Tertiary. The carbon is bound to what? 3 more carbons. Then for quaternary, the carbon is bound to what? 4 more carbons. So I'm going to use a case of saturated hydrocarbons. So if I have this, watch this now. Look at this now. Now look at this. What kind of carbon? Let's name these carbons. Each carbon here. What kind of carbon are they? Are they primary, secondary, tertiary, or quaternary? Remember. Now the reason why I used a double bond here is so that you understand that it is not. We don't designate primary, secondary, and tertiary to just alkanes alone. We also use the unsaturated. Look, I said I wanted to use saturated. Okay, for now. Okay, let me say it's 2 here. For now, let's deal with the saturated. Now look at this. What kind of carbon is this? This carbon is bonded to how many carbons? So once you see that it's bonded to 3 hydrogens, then you know that this is primary. But just count how many carbon is attached to. This carbon is attached to only one carbon, has direct connection with only one carbon. So that is why it is primary. About this carbon has direct connection with 1, 2, 3, 4 carbons. So we'll call it a quaternary carbon. Is that clear? A quaternary carbon. How about this carbon? Has direct connection to how many carbons? 1, 2, 1, 2, 3. So this will be a tertiary carbon. Is it clear? I'm going to tell you the use of this. Why do we name degrees of carbon? You'll soon get the use now. After this, we'll deal with carbocation. Is that time it will now make more sense to you? Now, this carbon is bonded to how many carbons? 1, 2, bonded with just 2 carbons. So this was secondary carbon. Is it clear now? So in fact, the best way to think of it is this. How many carbons how many carbon is that carbon bonded to? Is that clear? How many carbon is that carbon bonded to? And also, if you have bulky group around it too, so let's say for example I have chlorine attached to it. So for example, I attach chlorine here. This guy will become quaternary already, no longer this thing. Because this guy is a heavy group. Is that okay? No, maybe I'll give an example of that later. Let me give an example. Let me not scatter this first. I want to talk about saturated guys first. So this guy is secondary. Then this guy, no, let's talk about this guy. Here's the same. CH3, CH3. You see that? 3 hydrogens. Once there are 3 hydrogens, is what? This guy is secondary. This guy is primary. Is that clear now? Then how about this guy? Also primary. How about this guy? Also primary. How about this guy? Also primary. Now what if we now have something like this? Now, what kind of carbon is this? 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 Now looking at this, what kind of carbon will this be? This carbon is bound to one carbon only. So it will be a primary carbon. Is that clear? To be a primary carbon. This guy is bonded to 1, 2 carbon. Is what? A secondary carbon. This guy is bonded to 2 carbons. Secondary carbon. This guy, primary carbon. Do you now see now that even the unsaturation does not affect? Is that clear? So that's how you should know. That's how we designate primary, secondary, and tertiary carbon. Now, what's the use of this? Now, the use of this is in ions. Ions of carbon. There are 2 ions of carbon. We have so this is number 17. We have the carbocation. This is the positive ion of carbon. Positive ion of carbon. And this one, the second one is carbanion. This is the negative. This is the negative ion of carbon. Carbocation simply means a carbon carrying a positive charge. Carbon with what? Positive charge. While a carbanion means what? Carbon with negative charge. Now there is something you should know. Another name for carbanion is carbonium. Carbonium ion. Alright? So carbocation is carbocation. But carbanion is also called carbonium ion. Alright. Carbonium ion. Carbanion or carbonium ion. Now, when do we form a carbocation? First, what you should ask yourself is when do we form a positive charge? When do we have a positive charge? Remember when I ionized NaCl the other time, I showed you that Na plus and Cl minus is what we have. What does this mean? This means that sodium lost electron to who? To chlorine, right? So when an electron is lost, we have a positive charge. When an electron is gained, we have a negative charge. So setting that as your foundation, then you know that a carbocation is one that has a positive charge that shows that carbon has lost an electron. Is that okay? This one is carbon that has lost an electron, and this one is carbon that has gained electron. Lost electron, gained electron. But now, giving them degrees. So depending on the degrees, they are now, we usually now talk about their stability now, because because whether they will be formed or not, I'm sorry, that's what I want to say. Whether this carbocation or carbonyl will be formed or not, depend on their stability. It depends on what? On their stability. For example, let's begin with carbocation. For a carbocation, using these degrees of carbon, we will know stability. For example, a methyl carbocation does not pretty much form. Why does this not form? Because of stability. So this is very unstable. Very unstable, hence very unlikely to form. Very unstable, hence very unlikely to form. Very unlikely to form. How about if we have H? Now, what if we now have an R group attached to H, and H like this? What kind of carbon is this first? And then it's the carbocation. What kind of carbon is this? First, it is a secondary carbocation because this carbon, is a primary carbocation. Why? Because this carbon is attached to one more carbon. Because this is R group, okay, alkyl group, remember. So it is attached to one more carbon. So because it's attached to one more carbon somewhere here, this guy is a primary carbocation. Now this one is also unstable. So given in some instances it will not even form. Except now when does a primary carbocation form? I'll give you details on that later. But actually it is very unlikely to form too, because of it is unstable. In fact, except if there were suitable conditions, it will not form at all. At all, it is very unlikely to form as well. Now, why is it unstable? We are going to talk about it, okay? But first, know the ones that are stable, the ones that are unstable, or how their stability increases as we go down, or stability decreases. Is that clear? So, for example, if we have this, look at this guy. Now, keep in mind, how do you even recognize this? See, for those that might still not understand what carbocation is, see, it has lost an electron. How many bonds did I tell you must be around carbon? 4. How many bonds are you seeing around this guy? 1, 2, 3. So it means it has lost the electron to something. That's why I see a positive charge here. It has lost the third one, the fourth one that is supposed to use to form bond. It has lost it. It has lost the fourth one here. It has lost it. Okay? So what about this guy? This guy is now called a secondary carbocation. Do you understand? Now this one is quite stable. This one is what? Stable. Why is it stable? Because it has, I'll tell you why. Just come, just follow me. The next one is R, C bonded to another R, and C is bonded to another R. Okay? Then you see a carbocation. Now with this guy is more likely to form. More likely to form. Why? Because it is more stable. Tertiary carbocation. It is more, in fact, the most stable carbocation. Most stable carbocation. Is that clear? Now, why is it the most stable? The reason why it is most stable is because as you're looking at it, you can already see that that there are three heavy groups attached to it. Okay, so what are these groups now? Now, we call them organogens, okay? But let me not begin to bring in terms now yet. Now, here's what you should understand. That there is, because of the degree of substitution, let's talk about degrees of substitution. Now, this one is unsubstituted. It is not at all substituted. This one is more substituted, right? This one is substituted once. This one is substituted twice, right? And this one is substituted 3 times. Then you may ask, there is no tertiary carbocation, because when you have tertiary, it means that the carbon is fully substituted, right? Okay, now what do we mean by substitution? We mean that hydrogen has been substituted. That is, there is a different group apart from hydrogen attached to that carbon. So here, there is no other group attached to it, so we say it is not substituted at all. But this one is monosubstituted because there is another group attached to it. And keep in mind, like I said, it could be a Cl, it could be an halogen. This is also what? Substituted. Is that clear? So like I was saying, now what is now the use of these guys? Okay? Now you see the alkyl group, you see the alkyl group, they have a property that is, they have a property known as inductive effect. Now, it is not just them, electronegative atoms, okay, depending on the electronegativity of the group, they have they cause bond polarization. Yes, that's what I'm going to. They cause bond polarization. Now, just stay with me. Now, with respect to their inductive effect, I'm going to get to that later. Okay, we call these guys electron donating group. They are electron donating or electron releasing group. Now listen, keep this name in mind, because you are going to understand what the name means. But it will now make more sense to you when we get to the effect of bond polarization. So just stick with me. Now here's what happens. Now, by what is called hyperconjugation effect, there's no way we will not overlap these things. Okay, there's something called hyperconjugation also, and I'm going to deal with this after bond polarization. Just keep this in mind first. You see, this alkyl group, they are electron donating group. Now, what is a carbocation? A carbocation is a carbon that has lost electrons, right? So it is electron hungry, isn't it? It is electron hungry. So these hydrogens that are around it, they don't have sufficient amount of electron, right? The electron density is low, right? They don't have much supply of electron. I mean, hydrogen has only 1 electron. Is that okay? So because of that, it doesn't really help the carbocation. But compare that to this guy. Now you see this guy is still unstable though, but this R group is capable of doing something. Because this R group, if it was just a methyl group here, this methyl group is an electron donating group. What it does is that it pushes, because it is quite like more satisfied with the electrons it has, so it can push, because of there's an electron deficient center here. This carbocation also means what? Electron deficient center. Then carbanions also mean electron rich center. Carbocation gives notion of what? Electron deficiency. Gives the notion of electron deficiency, while carbanion gives the notion of electron richness. So it will be an electron rich center. That will be an electron deficient center. So this one that is an electron deficient center, what will happen is that this guy will donate electron density towards it. So the hydrogens too, the electron cloud will tilt towards it. Think of it that way. So because of that, this electron deficiency is not so will not be so what's it called now? Felt. It will not be so much felt. Do you understand? Think of it as say this guy has much more electron available in it, so he's able to supply for this guy. But of course, you cannot compare that to this guy. This guy has more substitution, so because of that, electron donation is coming from this end and from this end. We have a name for that, okay? We call it positive I effect, or positive inductive effect. So you will see that this guy is pushing electron density towards this guy. You understand? It's pushing electron density towards this guy because this guy is electron deficient. So then you cannot compare that to this. This one is almost full. Do you understand? So by two things, by electron donation and by hyperconjugation, I'll tell you what hyperconjugation is. They are able to stabilize this guy. This guy is more stable. So they donate electron density towards it to cover the electron deficiencies. Think of it as someone that is naked, but your friends have clothes, okay, and their clothes are big enough. So, for example, if you have only one friend, here, the one friend cannot cover you roundabout. The one friend can only do so much, so that you are not exposed, right? But if you are naked and you have two friends, one will cover you from the front, the other will cover you from the back. But of course, they cannot still go around as much, yeah. But think of if you don't have like three friends, these ones can go around. They can even form a triangle around you and they'll be able to cover your nakedness as much as possible. Do you understand now? So that's how to think of carbocation. Is that clear? Now, how about carbanion? When does the carbanion exist? The carbanion exists when there is what? A carbon-rich center. A carbon-rich center. Now, so this one is when electron is lost. A carbanion is formed when electron is what? Gained. When this guy gains an electron. For example, let's deal with acidic hydrogen in lability, or what do they call it? Labile alkynes being labile. The property of alkynes being labile. Now watch. Labile alkynes. And which alkynes are labile? Terminal alkynes, right? Terminal alkynes. Now what do they do? Now when you have a terminal alkyne like this, for example, when you have a terminal alkyne like this, this is just, when you have a terminal alkyne like this, when you have a terminal alkyne like this, you remember that, know that it is bonded to hydrogen here, right? Now here's the thing. This guy is able to lose this electron, lose the electron with this guy. I mean, not lose, sorry. Donate the electron out, okay, not, give up the hydrogen, let go of the hydrogen, that's what I wanted to say. Let go of the hydrogen. Why? Because it's able to form, so that it can be able to form an alkylide ion. An alkylide ion is a carbanion here. So this is a carbanion that is formed here by giving off hydrogen, and that's why we say it is acidic. Acidic because it's able to what? Give a positively charged hydrogen off. Is that okay? So I'm going to go into this now so that we can already see what these effects are. Now let's go to bond polarization, electronegativity. No, we are supposed to see cleavage, bond cleavage first. Let's see homolytic and heterolytic cleavage. So now, like I was saying, so that is about carbocation and carbanion. Carbanion being electron-rich center, okay? So, which makes this guy a conjugate base, which can now do what? So it will be a conjugate base that can take maybe a metal, for example, can attack it, and then it forms an alkylide, okay? So now, let's talk about bond cleavage. That's carbocation and carbanion. So let's quickly talk about bond cleavage. There's something I want to show you on that bond cleavage. Now, with bond cleavage, we have two types of cleavage, two types of bond. Bond cleavage means bond breaking. Okay, there are two ways a bond can break. A bond can break homolytically or break heterolytically. So there is heterolytic breakage, bond cleavage or fission. That's another name. Okay, fission, homolytic fission and heterolytic fission. Fission. Okay, fission is different from fusion. Okay. Now, homolytic. What does homolytic mean? Homo means same, right? Lytic means break, right? From lysis. So homo means same. It means that the atoms have the same electronegativity value. So for example, look at this bond between Cr and Cr, or between oxygen and oxygen. Look at this bond between them. Now these bonds can break, these atoms have the same electronegativity value. So because they have the same electronegativity value, when this bond wants to break, for example, if it were to break, it will break in such a way that both of them that are constituting that are engaged in the bond, they will get equal share of electron. So the way we represent it is we use half arrowhead. Okay, we use half arrowhead to represent these are a half arrowhead. Okay, think of this tail here as one electron leaving. The second arrowhead will look like this. Okay, so had it been it was a full leaving, full arrowhead, this one shows that only one atom gains both electrons. But this one half arrowhead shows that the two atoms get equal share of the electron. So for example, I told you that this bond represents 2 electrons, right? So by the time this bond breaks, what will happen is that one of the electrons will come on this guy. So you see, this half of the bond here shows that one electron has come to this guy and the other electron has come on this guy, so that this guy will now form free radicals. Okay, now these are called free radicals. Now, so these guys are necessary already to tell you that they are necessary for what? To initiate free radical reactions. Do you understand? So for example, there we have maybe CH4, for example, wanting to react with Cl2. So that's why it usually happens in the presence of UV light, okay, UV radiation. Why? Because the UV radiation is able to cause this kind of cleavage to happen to this guy. So this guy will, what initiates the steps is a free radical step, a free radical reaction. So this free radical will be formed by the presence of this UV light, by breaking this guy homolytically, and in that way we're able to form CH3Cl. And of course, because the presence of the free radicals, more free radicals, then they can continue to break more hydrogens, and then this thing continues, the reaction continues, plus Cl2, like that. This guy will break more, Cl will break, more free radicals are formed, and then you keep substituting. Do you understand? So this tells you it initiates substitution reactions. Okay, it can initiate some substitution reaction. Even for this guy, benzene substitution, the substitution reaction that we call it electrophilic aromatic substitution. Electrophilic aromatic substitution. All right. So even though this one here this guy will now, okay, HCl, more HCl. Okay, so that's primarily it. So that's homolytic fission for you. It happens between atoms of the same element. The atoms have equal electronegativity, so there is equal sharing of the electrons that are given off, and they are represented by half arrowheads. Okay, then free radicals are formed. Those are the properties. How about electrolytic fission? Now, this is a case where there are two different. So, for example, I have an arrow group with a fluorine, for example. Now, this guy, if this bond were to be broken, this guy will get Let's even use bromine. If this bond were to be broken, what will happen is that this guy, being more electronegative, is going to get all the electrons to itself. Is that okay? It's going to get all the electrons to itself. So this guy R will now become what? Positive. This guy will now become what? Negative. Do you understand now? So Br will now become what? Negative, because it has gained all the electrons to itself. It has gained all the electrons to itself. So there is unequal with electrolytic fission. There's unequal sharing of electrons occur with elements. So you see that a carbocation is formed here now. It occurs between atoms of different elements. There is an equal share of electron represented with full arrowhead, and produces formal charges on the elements, on the bonding atoms. Is that okay? So that's on cleavage. So quickly, let's now swiftly go to bond polarization. Bond polarization, so that we'll talk about the effect of bond polarization. So this cleavage is number 17. Now that's number 18. Number 18. So now let's go to number 19. That is bond polarization. Okay, I've already explained bond polarization, but let me just talk about it again. Bond polarization. Now, bond polarization is just this. Bond polarization is simply a dipole induced or polarity induced. Now, what is polarity first? Polarity simply means two poles, positive and negative pole. That's how to think about it, okay? That is the way you can remember it. Polarity simply means there are two poles. There is positive pole and there's a negative pole. So, bond polarity is the polarity that is induced due to bonding atoms, of different electronegativity values. Is that okay? Because the bonding atoms have different electronegativity values, then they are what? Because the bonding atoms have different electronegativity values, then the bond between them is polar, is a polar bond. So keep in mind that actually covalent bond is a non-polar bond, but it can be polarized. Do you understand? So bond polarization is simply the polarization of a covalent bond due to what? Electronegativity values between the bonding atoms. So for example, now what are the effects of this bonding atom, of this bond polarization? Those are the terms I will now talk about. In number 20 is an effect of bond polarization, not boiling point now, bond polarization. One of the effects is in number 20, I will talk about inductive effect. Inductive effect. Now what is inductive effect? Inductive effect is just the permanent dipole. Yeah, keep in mind that it's a permanent effect, okay? Permanent dipole induced on a sigma bond due to differences, the same thing, difference in electronegativity values of atoms. Difference in electronegativity of atoms, of bonding atoms. So for example, now let's now talk about the inductive effect really in proper. So let's say in our carbon, in our moiety, we have this guy, and is bonded to, let's use like chlorine, a good electronegative element. Now this guy, now what will happen is this. You see this chlorine that is bonded to it. These are all covalent bonds throughout. You already know that, right? But the case is such that this guy here, chlorine that is bonded to it here, has a high electronegativity value. The electronegativity value is as high as, I think, 3.0. While this guy, or 3 point something, or 3.1, while carbon has a electronegativity value of 2.5. So you will see that the electronegativity value is, the difference is far apart, right? So because of that, there is induction of polarity. So polarity is induced here so that this one will be partially negative because it is more electronegative, which means that it has more pull on electron, right? It will have more pull on electron towards itself than this one we have. Exactly. But now keep in mind, what inductive effect is now this. There is permanent dipole that is induced. So now, and that dipole is going to affect all other guys that are here, the other guys that are here. Now, the effect actually is not throughout the entire chain because the effect is distance dependent. Keep that in mind. The effect is what? Distance dependent. Okay? And the strength is measurable. It is measurable laboratorily. It is measurable, but it also depends on the strength of the organogen. This is going to be called the organogen. Strength of the organogen. I will explain what an organogen is. Now you see this guy as it is here. The inductive effect will be very strong on this one. So what you see, we use arrows to represent it. It's going to be very strong on this one, so that the electron is so drawn to this guy. But this guy, electrons are also going to be that because of that. See, listen, this is the way it is. I will link my video on inductive effect down in the description. Because this guy is very polar, it has very strong pull on electron. It's going to be pulling electron density a lot from this guy. Because of that, relative to this guy, this one will now feel electron hungry. Because of that, it's also be pulling electron density towards itself. And because of that, also this one too got pulling electron density towards itself. But what do you notice in my arrows? This one is very strong. This one is quite strong. This one is weak. Do you understand now? So the electron is distance dependent. It stops on the fourth carbon, or very negligible after the third carbon. It is usually very negligible after the third carbon. Now, the reason why I'm teaching you this inductive effect, because it has a role to play in determining the acidity or basicity of substances. Now, we're going to deal with the carrier. Let's deal with carrier after now. I'm not skipping you. I just want to show you something. Okay, that's number 21 now. Number 20 is an effect of bond polarization. I will talk about all the effects of bond polarization afterwards, but I want to show you the effect of this inductive effect. Okay, so we're going to be talking about carrier later. Okay, so the reason why I didn't list it here. That's why I'm having to write it down. I want to remember. So, but we have to deal with effect of bond polarization now first. So this guy, because of that, there is a partial positive charge induced on this guy. Very strong partial positive. But yeah, it is a weaker partial positive, and this one even weaker partial positive. So what do you notice? This one is very, very weak, and to be feeling weakly electropositive, quite electropositive, more electropositive. Do you understand? But because this one is very electronegative. So electron is spending more time with this guy. So because of that, this one will have a stronger pull on electron. Because of the problem this guy caused. It's pulling too much electron. So this guy will have to pull some more electron towards itself. And because of that, this one is pulling an electron towards itself. Do you understand now? So that's the way it is. Think of it as a tug of war. Now when in tug of war, you notice that the person that is closest to the line is one that is usually pulled into the line the most, right? Pulled if for example the people on this side win those guys, is the person that is in front that is usually pulled into the line, right? It's as if he experiences much of the force. Do you understand? Much of the impact of their force is more felt on him than the next guy, and the effect doing those as you go along the chain like that. So that's what we have with inductive effect. Now I'm going to tell you about the effect on acidity and basicity now. And of course, the effect on carbanion, that's why I did not clean this up. The effect on carbanion and carbocation. Okay? Let me talk about the second effect I like to talk about is electromeric effect. I'll make it short. Electromeric effect. Now, electromeric effect is just now this one is inductive effect is a permanent effect. Electromeric effect is a temporary effect. Now, why is it a temporary effect? It's a temporary effect because it only happens at the approaching of an organogen, at the approaching of an organogen. So it means that this thing only happens when an organogen, when an organogen approaches. And an organogen is the guy that wants to react with this guy, or the guy that is already reacting with this guy. So for example, this is an organogen here because already reacted with this guy. So it's the one that is causing the whatever effect that we are talking about here that's causing it to happen. So because of that, we call it an organogen. It's a special group on that chain. So for example, if an electrophile, for example, approaches, okay, let's also talk about, let me quickly talk about electrophile. We'll come back to this now so that you understand the terms. Let me quickly talk about an electrophile. So this will be like 22. No, let this be 22. We'll come back. We've not done 21, okay? I'm skipping it because I don't want to forget. 22 is an electrophile. Mommy, FSHMB, right? Okay. Okay, thank you. So we have an electrophile, and we have what is called a nucleophile. That's number 23. A nucleophile. Now I'll teach you the way I normally remember this thing. It's very simple. See, electro means electron, right? Electricity, electron. Phile, what does phile mean? Phileo. Phileo means love, right? It's a Greek for love, Greek word for love. So it means that electrophile are what? Electron loving. Electron loving. Is that okay? So then nucleophile is what? Nucleo means nucleus, right? Nucleus loving. So these ones are positive charge loving. Now, why do we call them nucleophile, not proteophile or whatever? The reason is because in the nucleus is where you have positive charge, right? The nucleus is primarily positively charged. The nucleus is positively charged. So because of that, they are attracted to the nucleus. So if they are attracted to the nucleus, now this is where students get confused. So remember, nucleus means positive charge loving. That is nucleus loving because the nucleus is positive. So it means they, now, and in electrostatic law, positive and negative do what? Attract. So because of that, these guys are negatively charged. They are negatively charged. So that's why they are attracted to the nucleus. So negatively charged organogens will be what? So for example, OH will be what? OH minus will be what? A nucleophile. But electrophile will be what? Positively charged. They will be positively charged. Why? Because they are electron loving. Do you understand? It means that they are seeking to coordinate with an electron. Do you understand? They are seeking to coordinate with something that is negative. Okay? So this one is what? Positively charged. Do you understand now? They are positively charged because they are electron loving. Now, so like I was saying, look at the case of, let's look at the case of, which chemical reaction should I use now? Do you remember Markovnikov rule? Yes. I want to talk about electromeric effect. Should I use Markovnikov rule? At the approaching of an organogen, yeah. There is, okay, see, let me show you. There are two types of, I didn't talk about this. There are two types of inductive effects. Types of inductive effect. I've mentioned this before, okay? So maybe I will link the video in the description. There's the plus I effect and there is the minus I effect. Minus I effect. Now, what is the plus I effect? The plus I effect, you remember that in this case where I talked about electron density being pulled away from the chain. Oh, okay? This one is the negative I effect. Because electron is being pulled away from the chain. But in the plus I effect, electron is being donated towards the chain. Is that clear? So for example, if this were, we have something like this, and then we now have R group, maybe there's a carbon here, and then we now have R group like this. Now looking at this guy, the electron, you're back. The electron, now looking at this guy, now you see these are alkyl groups, okay? I put prime and prime to show that they might be different. Now they cause what is called the plus I effect. The plus I effect is caused by plus I group. What are the plus I groups? They are the electron donating group. I mentioned that somewhere just now. They are the electron donating group. Why? Because they make electron density available in a chain. In a chain. Let me check that first. They make electron density appear in the chain, available in the chain. So they push electron density into the chain. While a negative I group like chlorine, negative I groups, they are halogens. Plus I groups, they are like amine. No, amine. Amine is a nitro group will be, because amine, yes, amine gives now. Amine gives. So amine is going to be a plus I group. Oh, amine has a lone pair. Okay, so what it does is it can donate that lone pair. So it will be a negative. It donates electron. So it will be a positive ion group. So we have amine group is electron donating. Alkyl groups generally. But there is also order. Okay, there is also degree or strength of the I groups. So for example, a methyl group will not be as strong, will not have as much inductive effect as, it will not have as much positive inductive effect as a CH2CH3, okay? And this one will not have as much as a CH2CH3. Do you understand now? Of course, the degree of substitution too matters. So this one, so a primary will not also have as much as a secondary, and this one will not have as much as a tertiary. Do you understand now? All right. So that tells you that. But of course, when we talk about this is their own effect on the chain. Now, the effect on them is in the opposite order. What that means is that a negative, this guy now, this nucleophile will not affect a chain that has tertiary as much as it will affect a chain that has secondary carbon. And it will not affect a chain that will have tertiary as much as it will affect secondary. And it will affect primary the most. That's what I'm talking about. Inductive effect, negative inductive effect on them is in the reverse order. But positive effect, inductive effect on them, their own effect on, because they are the positive I group, right? Their own effect on a chain is in this order. That is, this one cannot affect much, will not donate much electron. This one will donate more, this one will donate more electron density. Is that clear now? So that's what I'm trying to talk about. So halogens, nitro group, they are negative I group. COH, they are negative I groups. Now, I was talking about, so we now know nucleophile and electrophile. So the electromeric effect now, for the electromeric, so when an organogen attacks, so for example, look at this guy. There are two types of electromeric effect too. We use plus E to represent it and minus E to represent it. So let me show you, you are going to understand it. Watch. We have a C double bound to O, okay? Now, let's use a case where C double bound Now, this guy is to be approached by this organogen. Now, what other organogen is this? This will be what? An electrophile. So, electrophile means it is electron loving, right? Okay, so what you want to do is that you want to go and coordinate to this point. Now, what will happen is this. As this guy approaches, here's what electromagnetic effect is. Once this guy approaches to attack it, you know, this is in addition reaction. This is our addition reaction of hydrogen. I want to talk about addition reaction of hydrogen. So when this guy approaches, what will first happen is that this bond will cleave, okay? Now there are two directions in which the bond can cleave. It's either it cleaves here or cleaves here. Now if this bond cleaves here, if the bond cleaves here, what will happen is that at this point we have a slight negative charge, and this point here, a partial, this one will have a formal negative charge, this one will have a formal positive charge. So this guy will now be attracted to this point here. Is that okay? This one will now be attracted to this point. This guy will be attracted to this point. So now listen. If the organogen and where the bond cleaves are, so this one is attracted to the point, you know I told you the bond will cleave here. If the organogen goes to the point where the bond cleaves, that is positive electromagnetic effect. But if the organogen goes to the opposite direction of where the bond cleaves, that's negative. For example, let's say this guy was cyano group, nitrile group. By the time the bond, this double bond cleaves here, okay, then we have lone pair here. This guy will come and attach itself here. Exactly now. So come and do what? Attach itself here such that the bond cleaved on this place, but this guy attached to the other side. So this is a negative E effect, negative electromagnetic effect. All right. This is just foundation, okay? So that's why I don't know if I'm being simplistic enough. I don't even know, but try as much as possible to understand. For those of you that have taken it before, okay? But if you have not taken it before, that's just the way to understand it. That there will be no reaction of cleaving here. There will be no movement of electrons. There will be no movement of electrons except there is an approaching organogen. Once the organogen approaches, then there is a cleaving of the pi bond, and then the pi electrons move to one of the molecules. Is that okay? If the molecule, the organogen now attacks on the bond that is being, or attacks on the atom that gets the lone pair, that is positive. They go to the same place. Electron go to the same place as the guy that attacks. But if the organogen goes to the opposite direction of the electron pair, then that is a negative E effect. Is that clear? All right. So that's the electromagnetic effect for you. So then let's talk about resonance effect. Then we'll now go to carrier. That's number 24. Okay, I will have to redraw this because there is no space again, and I want to show you carbocation stabilization. Oh, let me just explain. That's 23, 24. Let's talk about mesomeric effect. Now, mesomeric effect is also called resonance effect. But keep in mind that resonance is not all mesomeric effect. For example, so the way it is such that mesomeric effect is a type of resonance effect, of resonance. Mesomeric effect is a type of resonance. But resonance, so not all resonance are mesomeric effect, and not all but all mesomeric are resonance. All mesomeric effect are resonance. but not all resonance are mesomeric effect. Exactly. Right. So here's what happens. In resonance effect, it's just about due to the presence of a more electronegative element, for example, there is induction of polarity. So, for example, there is, I say induction of polarity. There is movement of pi electrons. Sorry. So this one is displacement. This one is temporary displacement of temporary displacement of pi electrons due to the presence of an organogen, while this one is delocalization of pi electrons. Delocalization of what? Pi electrons. So now keep in mind that, let me first use an alkene, for example. Now looking at this carbon here, sorry, I want to use a conjugated system. Now there's something that can happen here. This carbon here is sp2, sp2. Now when there is conjugation simply means there is alternating single, double bond. So what will happen is this, that this bond, these pi electrons here, they can move, okay? So we define mesomeric effect as the stability effect brought about, or stabilization brought about by what? The localization of pi electrons about a given number of atoms. Stabilization is brought about by what? The localization of pi electrons over a given number of atoms. You can write that down. So see, this is what happens. You see this guy is more stable. This guy is more stable than this guy. 1, 2, 3, like this. Is more stable than this guy. This will be 1, 2, 3, 4, 5, 6. This will be hex 1, 2, 3, hexa 1, 3, diene. While this one is hexa 1, 2, 3, 4, 1, 4, diene. Hexa 1, 3 diene is more stable than hexa 1, 4 diene. Why? Because hexa 1, 4 diene is an isolated alkene. This one is a conjugated alkene. So in a conjugated system, what happens? What happens is that these pi electrons cannot, think of it as you are carrying a burden, and you have friends around you that can help you to bear the burden with you. With that, the burden will not be so much on you again. I hope you understand that. The burden will not be as much as if you were the only one to bear the burden alone. Do you understand? If you are the only one to bear the burden alone. Okay? So what will happen is that here, this pi bond, when is it conjugated? When we have alternating single, double. So what can happen is that this pi bond can resonate here in what we call mesomeric effect. Keep in mind that this is happening because of the way the molecule is formed. So the resonance contributing structure that I can draw for this will look like this. 1, 2, 3, 4, 5. So this one has come here to form like this. This one has come here to form like this. Keeping in mind that it is still what? Alternating single, double bond. Exactly. So what will happen is that this guy will be now. These are resonance, we call them resonance contributing structures. That is, the structure is never exactly in reality, never like this, and never in reality exactly like this. It is somewhere in between. So what do I mean by somewhere in between? So instead of having the pi bonds be exactly on carbon 2 here, or be exactly on carbon 1 and carbon 3 here, no, that's not what will happen. What will happen is that, in reality, what we have is this. 1, 2, 3, 4, 5. So in reality, what we have is this bond will be spread across like this. This pi electrons are there. So you see that there is more space to move around for the electrons. So because of that, the burden is lower on this guy, hence this guy is more stable. Do you understand now? So that's what mesomeric effect is. And of course, there's positive mesomeric effect and there's negative mesomeric. Negative mesomeric effect. So for the plus M effect, or some people might say it's plus R effect, okay? Plus M and negative M effect. Plus M effect is just brought about by electron donating group, the same way. Minus M effect is what by electron withdrawing group. So for example, if I have a phenol, for example, no, if I have, let's say, let's use an aniline. Let's use aniline. Benzinamine. Okay, that's an amine group attached to benzene. Like it's easier to visualize. Okay, it's easier to use it to teach. I mean, we can use other things too, but since I already told you that this guy is an electron donating group, what does it do? So, because it has a lone pair, how do I know it has a lone pair? If you count the octet structure, this guy is bonded to two H's, right? So 1, 2, 3, 4, 5, 6. For it to have 8, it needs 2 more electrons. So for it to be complete octet, it needs 2 more electrons there. So this lone pair here, okay, it can use it to form a bond with this guy. Exactly. So in which case, if it uses it to form a bond with this guy, what will happen? This bond, resonance begins to occur, right? Resonance begins. And what is that? How does that resonance happen? That double bond that was formed here before will now come here. Is that clear? So since this lone pair is coming here, this bond will now come here. By the time the bond comes here, the resonance contributing structure that you will find, you will get is this guy. The resonance contributing structure will be this guy. Now these pi electrons will come here, right? The pi electrons will come here, and they're going to give us a negative charge here, right? And then of course leaving this one with a what? With a positive charge. Is that clear now? That guy will have a positive charge, this guy will have a negative charge. Then of course your double bond is here, your double bond is here. Now one thing can also happen that this guy, this pi bond can come and attack this end, and when it attacks, this one also attacks here. This one falls on this carbon rather. Falls on this carbon. So by the time it falls on this carbon, what do you see? There's something I'm going to show you here. Watch something. Still double bond. Now this guy, this pi electron, from this pi bond, the pi electrons will move here. Is that okay? Give us a formal negative charge, not the partial. Then this one, this one will collapse here and form this, and of course there is still this here. Now notice that, let me draw the last resonance structure. The last resonance structure, there is one more resonance structure where this guy will attack this place. Once this guy attacks here, well, I want you to notice something. When this guy attacks here, this guy, once he attacks here, this one will also fall on this. When it falls on that, we have NH2 double bound to this. I want you to notice something. See, once our double bond forms here, I want you to notice where our double bond is forming now. Our double bond, our pi electrons kept forming at ortho positions. Yes or no? So that's why when chemical reactions like this want to happen with this guy, it's going to designate two major positions, ortho position and what? Para position. So throughout you see that there was no meta position formed for the anion, right? So for the carbanion that is formed here, it's forming on para and ortho position. So that is so aniline here, the resonance it gives us an ortho and para designator. Ortho para designator. It doesn't give a meta, it's not a meta designator. But of course, if it was an electron withdrawing group, so for example, where we have this, for example, what will happen is that this one might withdraw its electron, in which case, when it forms the bond, When it withdraws its electron, then this guy will have to come and form bond outside. This one will have to move up. Do you understand? So you see that it's withdrawing electron from here. So this is negative M effect, and this is positive M effect. All right, so I'll have to move from here to another class because they want to take care of this place. So, but in the meantime, we're going to talk about steric effect, then alkane. No, radiochemistry. Let's talk about those other terms. So you now watch my video on alkane. I don't want to do, I don't want to talk about it here again. Radiochemistry. So I'm just going to wrap this up quickly. We have already talked about those effects of bond polarization. Now there is also something called steric effect. Now what is steric? You will most likely see it as steric hindrance. That will be number 25, steric hindrance. Now steric hindrance is basically when there is bulky group attached to a molecule. Bulky group attached to a molecule leading to the hindrance or opposition of approaching groups. Do you understand? Any group, hindrance of an organogen. So if there is a bulky group attached to a molecule, okay, so for example, when there is a bulky group attached to a molecule, some electrophile might not be able to attack, okay? Do you understand? So for example, if this molecule is like this, if there is a molecule like this, maybe there is a carbocation that is formed like this, you know this guy will be stable, right? And there is an approaching organogen, for example. Once you approach, now you cannot really attack because it is sterically hindered, okay? Now look at this, for example, if this was hydrogen, okay, this organogen here that is approaching cannot attack from the back because there are big groups at the back that will block it. Much bigger is even if we now have, let's say we have a third butyl here, for example. This is a propyl, this is a third butyl. So that's CH3, CH to CH3, CH3, CH3. No, C to CH3, CH3, CH3. So this is a third butyl. So a third butyl is this cross that I put here. So if you have this here, for example, this one cannot attack from this back because this is a bulky group, okay, that will hinder the base. Is that okay? We say the base is sterically hindered. That is, this group cannot attack from the back. For this guy to be able to attack at all, it will come from somewhere around here to attack. Do you understand? Because this is a very small group that is attached here. So this is the only place it can attack it. So, but that's basically steric hindrance, when there's bulky group that is shielding, okay? But when there's bulky group attached to a substance, to an atom too, they are able to, by hyperconjugation effect, they're able to, by hyperconjugation effect, help stabilize the carbocation. Yes, and this carbocation that is formed because they will donate electron density towards it. Hyperconjugation effect is also called no bond resonance. Okay. Now there's an exam question that I saw where they said which of these is hyperconjugable. Because of the length of this video, I will not be doing that. I will release another video on hyperconjugation effect and maybe those other effects that I have not explained at all before. I will release them later. Now number 27. Let's talk about the acidity here. Acidity that I talked about using carrier. No, that was question number 21. So we are going backwards, okay, to question number 21. So for example, what they just test you with is this carrier. I actually saw this mnemonic on leahforsci.com where she used the carrier because most one that I see in textbook is Ariel, okay? She used this, okay? So, and what she said, the C represented charge, according to her. Then, of course, we already know that the A represents atom, R represents resonance. Resonance is easy to spot. Inductive effect is one that is not so easy to spot, okay? And O represents orbital, the orbital in which we can find the guy. So this is used to test for acidity. So for example, if I ask you which of these is more acidic, look at this molecule here. And I say between this one and this one. So which of these is more acidic? Molecule A and B. Which one is more acidic? Is it this guy or this guy? Now we'll check. Is there charge here? And there's no charge. Both of them are neutral. So we'll come and check. The next thing to check is the atom. That's what we use this carrier for. Is the atom. Now the atom bearing this guy is C. It's carbon, right? It's carbon that is bearing hydrogen here. We know that this alkyne is terminal and it is acidic. But which one is more acidic? Okay? Which is more acidic? I'm covering it now because I promised to cover it, and I've just done it in another video. Which one is more acidic? Now this guy is more, this guy is acidic, this guy is acidic, okay? But we want to know which one is more acidic. Now this carbon here, this is, now we checked on whether there was a charge, there's no charge. Then A represents atom. The atom bearing this O group here, you know there are two lone pairs here. The atom bearing it is electronegative. So we'll check for the electronegativity of those atoms. Now, oxygen is very electronegative compared to the atom that is bearing this hydrogen here, is carbon. Carbon is less electronegative. So because of that at all, alone, this one will be more acidic. Another one that I commonly see in exams is this. Now look at this example for instance. Let's say you see something like this. Now, what if you see something like this? There's another question, another type of question, like this one. See, what if you see something like this? And you now see another one like this. OH attached, okay? But then this guy is substituted. So which one will be more acidic between these two? Is it the guy that has OH attached to it? And both of them have OH attached to them. So let's go. Using charges, no charge at all. Using the atom that this OH is attached to is carbon. The atom that this OH is attached to is a carbon. How about this guy? So that's the atom. So the same type of atom, carbon. The OH is attached to the carbon. So these are they've passed this to. Let's talk about resonance. Now, is there any resonance here? No resonance here at all. There is no resonance here. So because there is no resonance here, then we can not use R. So let's go to inductive effect. So now let's check for inductive effect. Now what's going to happen here? The one that will be more acidic is the one that can form a more stable conjugate base. The more stable conjugate base. So that if our conjugate base here is going to look like this, that the hydrogen will be given away such that with this one, the conjugate base will look something like this. We have 0 O minus because of 1, 2, there were 2 charges, 2 electrons before, then there will be 2 more electrons. Now, then this one will also will look something like this. Minus, we have 1, 2, 3, 4, 5, 6. Now, look at this. How do we know which one is more stable here? Now, we'll know that you can already see here that this guy and this guy, we can go back to charges now. Both of them are negative. So, how do we know which one will be more stable? Now, the more stable one is the more acidic one, okay? The more stable conjugate is the more acidic one. So, why do we say that? Because it means that if it's more stable, it means that if the conjugate base can be more stable, then it means that it will readily become a conjugate base. That is, it readily give off hydrogen. So it readily donates hydrogen, so it means it's more acidic. So which one is more acidic? Is it this guy or this guy? Now, why would this guy? Now, which one will be more acidic? Now, looking at this, now this negative charge here is an abundance of electron, right? So which one Now, looking at this, now this one has electron abundance, right? It's electron rich. So it means that the group here, it will donate electron density into the group here, right? It will donate electron density, isn't it? So here to donate electron density here. But already this guy is donating, now this guy is attached to another group that is an electron donating group. So as it's an electron donating group, this one is also an electron donating group. Because of that, because of positive I effect, because of positive I effect, this one will be more electronegative. This one will be more acidic than this guy because of positive I effect. Okay? Because of positive I effect. And of course, because this positive effect here is causing this guy to donate electron density towards here. This one too is donating electron density towards this side, the same carbon. So there's this carbon is not a group that withdraws electrons, it's not an electron withdrawing group. So it cannot help to stabilize this guy, this negative charge as much. Do you understand now? It cannot help to stabilize this charge as much. Unlike this one that doesn't have any group that is donating more electron density. So because of that, because here there is too much electron density donated here there is not so much electron density donated here. So because of that, this guy is more stable, and because of that, it's more acidic. Compare that to this one. I think this is a better example. This one I want to give now. Now let me give using this one for example. Now if you see this, look at this guy. You see? This, if we use carriers still, we use charge. There's no charge. Atom. The atom bearing the acidic portion here, because it's an acid already. The atom bearing the acidic portion here is oxygen. So here too is oxygen. Okay? The acidic hydrogen. So it's oxygen. So they are both the same, equal there. How about resonance? They have the same resonance resonance stabilization effect, because by the time this guy resonates here, the double bond, the resonance hybrid will look something like this. The resonance hybrid will look something like this, where the pi electron is resonating across the two bonds, the two atoms, the two hydrogen, oxygens there. So now, these guys are primarily the same. And I say, what if I added chlorine here, for example? So what if I added chlorine to this one? Which one will be more electronegative? Now, actually, if we use resonance, we will not still get the answer, okay? Now, if we use inductive effect, you can get the answer. The reason why I'm targeting inductive effect is because I just explained it to you. I want you to see the effect under this thing. Now, the inductive effect that helps, inductive effect is going to help this guy to be more acidic. Why is that? The reason is this, that this chlorine is an electron withdrawing group. So the moment this guy loses this charge, this hydrogen, this guy becomes negatively charged. Okay, so this guy is an electron withdrawing group. So already is going to be pulling electron density towards itself. Okay, it's going to be pulling electron density towards itself. So because of that, it will help to stabilize the two. Negative charge means abundance of electron, right? That is electron rich. So this electron richness will be stabilized by someone that is already wanting more, that is wanting it to be stable, more stable than this guy. Is that okay? So this one is more acidic. So the guy that has, of course, if this guy was far away from it, compare this now, compare this. Now compare this to this. Which one will be more acidic? This time, this guy will be more acidic than this guy. Why? Because this guy is more electronegative. So because of that, the electron density is drawn more towards this guy the moment this guy loses his hydrogen. Is that clear? So that's that on acidity. Now let's talk about 27. Let's talk about some reactions. No, before we talk about some reactions, let's talk about chirality. Before we talk about chirality, let's talk about, I've left that class, that's why. I can't remember now. Let's talk about, which other term confuses students? Conformation analysis. Conformational analysis. So this one is just talking about the different orientation, spatial orientation of atoms, okay? Spatial orientation of atoms. Think of it as we are studying the radiochemistry already. Okay, even though there's still something I want to teach you under regiochemistry, okay, where we talk about stereo centers. Now, the spatial orientation is like this. We use Newman projection to represent them. So I'm going to be using an alkane in this case. Okay, we have different conformations. We have what is called, there are two extremes of conformation. We have staggered, two types of conformation: staggered conformation, staggered and eclipse. Staggered and eclipse conformation. Now, what is staggered conformation? Now, what we are doing is this. We are going to be using a molecule that looks like this. Look at this molecule. This is the way the Newman projection of this guy. Let me draw this molecule first. You see this guy? This is, depending on the molecule, let me add CH3 here. Let me add Br here. Let me add H here. Let me add Cl here. Let me add CH3 here. Let me add H here. See, look at this guy. The name of this molecule is 1, 2, 3, 4. That is butane. So 2 bromo, 3 chloro butane. Okay? Now this guy, I want to show you in the Newman projection. In the Newman projection, I'm going to twist it in such a way that, his line is like this, right? I'm going to turn it such that it will be facing me here. So if it's facing me here, it's going to look like this. So that it's going to look like this. This one will be in front. This side that is in front, we'll put it here like this. So what is on top? Cl. What is here? CH3. CH3. What is here? H. Then the one at the back, we use a circle to represent it, the guy at the back, so that this one will be projecting from here. Let me put this one like this. This is another type of conformation, okay? Then put this one. It means it has twisted like this, so hydrogen will come here, then bromine would have gone this direction. Okay, now I want you to see this. You see, with this conformation analysis, you will understand steric hindrance too. We also understand interaction between molecules, okay? Interaction between atoms on the same molecule, rather. Atoms on the same molecule. So, for example, as this guy is like this here, as this guy is. Now, this conformation is called staggered, okay? This is staggered, but not fully staggered. Why is it staggered? Because the bulky groups, now what are the bulky groups here? CH3 is bulky, CH3 is bulky. This guy is quite big, this guy is quite big. They are as far away as, they are moderately far away from each other. They are moderately far away from each other. So we call it staggered conformation, okay? It is a lower energy state than eclipsed conformation. So I like to start with the eclipse. So what we want to do is, we want to rotate this molecule. We want to rotate it as much as possible. So if we rotate it, the first conformation we'll get, the first type of conformation we'll get, if we rotate, let me redraw it. I want to draw it like this, such that CH3. I want to put the CH3 on top. So if I put that like that, chlorine will come like this, and hydrogen will be like this. Then at the back, so this one means it's coming from the back. These bonds are at the back. So this one is still like this. Let's leave this one the way they were. So, but this time, look at this now. I want to rotate. I'll be rotating the guy at the back. This one, this bond at the back. Keep in mind that that's another this thing of sp3 hybridization. It leads to sigma bonds that can allow for free rotation. So the bond can be rotated. So since the bond can be rotated, we are going to rotate it. Now this conformation you are seeing here, this one is actually called staggered because it's in between. These guys are quite far away from each other. But if you compare to this one where they are closer, okay, this still pretty much like staggered, but compared to this one, compared to something like this. I now move this guy close to this guy, pretty much closer like this, such as this one is coming here, BR is here, H is here. Now this one is called gauche conformation. Gauche is a type of staggered, okay, or in between staggered and eclipsed, only that it is not fully eclipsed. Now let me show you proper fully eclipsed conformation. Fully eclipsed conformation will look something like this, where I have rotated this guy totally such that this guy is just behind this other guy, CH3, and this guy is just behind the CL, and this guy is, sorry, is at the back. It's supposed to be on this cycle. And this one is just here. So you see that the heavy groups are interacting with each other. They are interacting with each other here. So this is what is called fully eclipsed conformation. This is fully eclipsed conformation. So this one has the highest energy. While this one has the lowest energy. Anti-staggered has the lowest energy. I've not drawn that. Let me show you anti-staggered. These are the bulky groups, right? So what if I could do this? Now notice the bulky groups are the farthest away from each other as they can be. They are farthest away from each other as they can be. So because of that, we call this anti-staggered. So this is the lowest energy that this structure, this molecule can have, lowest energy. But this is the highest energy state that it can have. Why? Because it takes more, because they'll be interacting here, and electrons will be repelling. And this is not stable. This will not be as stable as this. So this will be the most stable, also most stable conformation. Okay. Let's quickly talk about chirality. I'm not tired, in Jesus' name. Let's quickly talk about chirality. Question, number 28. Chirality. So chirality is just about the possession of 4 bonds. Oh, we've not even talked about isomerism. 28, sorry. Number 28. Number 28. So in number 29, I'll talk about isomerism. Then 30, I'll now end up with reactions. Let's end up with reactions. So chirality is just the presence of 4 different groups around an atom, around a carbon atom. Okay, so what that looks like is this. So when there are 4 different groups, that carbon will be called the chiral carbon. Okay, it gives it a chiral center. Now, what that looks like is this. There will be 4 different groups: R1, R2, maybe OH, maybe R. So look at this. So this carbon here is said to be chiral. So this is said to be the chiral center, or the chiral carbon. So now what is the effect of this, or what is the significance of this? Its significance is that it influences the stereochemistry of this guy. And what's the stereochemistry of this guy? It's going to impact what is called optical isomerism on it. It's going to have optical isomerism. It's going to have optical isomerism. So it means that you have to understand what isomerism is. In optical isomerism is just this guy is going to have another molecule that will have mirror image of itself. So there is going to be another molecule that will look like this R here. Then this R will look like it were here, and this one will not look like it were here, and then the OH is here. So you see that these are mirror images of each other, right? These are mirror images of each other. So if we are defining this molecule with respect to this guy, and it's on the right, it will be called the D group. This one will be called the L group. The D stands for dextrorotatory. In my video on isomerism, I will link in the description. I've talked about this. This one is called livo-rotatory. So, but basically, the kind of question you will see on chirality is, so keep in mind, when there's a double bond there, then it's not chiral, okay? So let's check. Which of these molecules are chiral? Which of these carbons are chiral? All right, let's see. So this CH3 here, is it chiral? No, this is not chiral. Now let's look at this guy here. Is it chiral? This is Br group attached. H group will be attached here. CH3 is attached here, and another different group is there. So this is chiral. Is this one chiral? So if you ask how many chiral centers are on this molecule, is this one chiral? Let's see. Cl is attached. H is attached here. Another group here. Another group here. Chiral. Yes, this chiral. There's a double bond here, not chiral. Here. There must be 4 different groups. That's the definition, okay? So that's how to just look at it. Now, is this chiral? OH group, different group, and H group here, chiral. So how many chiral centers do we have? 3 chirality centers. 3 centers of chirality, or 3 chiral centers. So that is for that, for chirality, when there are 4 different groups attached to a carbon. Is that okay? Let's look at isomerism quickly. Isomerism is just the existence of 2 molecules with the same molecular formula but different structural formula. The word iso means the same. Mer will refer to like unit, okay? So similar units. So they have the same molecular formula but different structural formula. Okay? I'll just give one example here. So for example, look at this guy. Look at this guy. Butanol, for example. This is positional isomerism. Butanol and butanol. Both of them will have the formula C4H7O or something, or H8O rather. This one, so the formula, the molecular formula also was C4H8O. But if you want to draw the structure, this one will look like this. This is butanol, so it will look like this. OH will be on the first carbon. Is that clear? But for this one, butanol now. OH will be on this second carbon. So do you see that the position has changed? This is called positional isomerism. There are different types of isomerism, and I've discussed in the video I will link in the description below. But I just wanted you to know what isomerism is. You see, this one is on carbon 1 here, it could be here, it could be here, and this one is on carbon 2. So they are different, but they look alike. Is it clear? So that is positional isomerism. That's what isomerism is. The same molecular formula, but different structural formula. Then number 30, which is the last, let's talk about the chemical reactions. Some chemical reactions. So general chemical reaction that you must know is combustion reaction. Combustion reaction, when you hear combustion reaction, is just reaction of that guy, that hydrocarbon or that organic compound with oxygen. When we call it combustion, it means that oxygen is supplied in as much extent as possible, so that the product is always carbon dioxide and water. Is that okay? This is very important point.